Good afternoon. I'm going to continue now with a discussion of elementary thermodynamics based on the ideal gas. Okay? Now we're going to talk about heat engines. Specifically, we will look at the Carnot cycle. Whatever a cycle is, we will talk about. We will introduce, we will come across this idea of entropy was stumbled on by researchers in a way. And we'll talk about the second law of thermodynamics. And some people involved here, I always refer to the people. Nicholas Carnot, Sadie Carnot they call him, I don't know why. 1796 to 1832. Rudolf Clausius, Carnot was French, Clausius is German, I think. Yeah, I think so. 1822 to 1888. 1888, my grandmother was 8 years old. William Thomson, sometimes called Lord Kelvin, he was from Belfast. I forget the years of his existence. Actually, I do know that he opposed home rule. I think I gave Lord Kelvin's years of existence in a previous lecture. Ludwig Boltzmann, okay? Boltzmann has written on his tomb, S equals K log Z. S is going to be the entropy thing that we're going to come across. This is approached statistically though. K is the usual Boltzmann constant. Ln stands for Napierian logs, not natural logs, Napierian. And Z is the number of microstates associated with a macrostate with entropy S, whatever that means. We'll talk about later. Work done on the system. Now, first of all, let's look at the ideal gas law. Remind us. The beginning of everything. Now these are a little bit casually written. They stand for changes in work, changes in heat, changes in internal energy. For example, delta V, a change in volume. Delta Q could be an amount of heat used to heat up a certain mass of substance with specific heat capacity, C, changing it from a temperature T2 to T1. However, these deltas, let's talk about them, are small compared to what we regard as a reservoir. The little delta Q's are small changes in the system, this system here, the reservoir, containing a huge amount of heat, Q. Amount of heat, yes. Amount of heat is measured in joules. Temperature is a measure not of amount of heat. Temperature is a measure of the amount of hotness, if you like, the mean kinetic energy in a substance. Delta U is the internal energy, and an increment of internal energy, delta U, just depends on the change in temperature. Yeah? You change the temperature, you change the internal energy, you change the internal energy, you change the temperature. However, one way or another, we can change the internal energy by putting heat into it or doing work on it. Now just putting in P equals constant for a moment. Now this is the first law, of course. First law of thermodynamics. Now the 3 here was due to the number of degrees of freedom in the systems. Let's just talk about that. the only monatomic gases are the following. Helium, neon, argon, krypton, radon, and xenon, and you recognize these to be the noble gases. Diatomic would be like this. Oxygen, hydrogen, carbon monoxide, chlorine, what else? Nitrogen. That's about it. Now I put in carbon monoxide here because it's going to look a little bit different. It's not a perfect dumbbell, whereas these ones are. These diatomic molecules we can envision as being dumbbell shaped, and these are monatomic. Now the degrees of freedom of the monatomic atoms in a gas are just those of the x, y, and z axis. I didn't have to put those in the right way. Maybe. No more, I forget. One way or another, the three spatial degrees of freedom, up, down, and across. Okay? Now that's the way, the directions in which this guy can move. Now if we take a diatomic gas, I'll do it right this time, and we situate it, let's say, such that its center of mass is on the origin. Here's one of the atoms here, here's one of the atoms here. It could be a hydrogen atom, could be any of those assorted ones. What are the degrees of freedom? Well, there are three translational degrees of freedom. But there are also this degree of freedom. Rotation in the ZY plane of the dumbbell. Rotation in the XY plane of the dumbbell, around like this. Okay? And you say, what about rotation in the Y plane? Of course there's a rotation in the Y plane, degree of freedom. Like this. Rotation in the Y plane is neglected because I, rotating in the, let's see, what plane is that? Y, Z. Now we did the YZ, so rotating in this is the ZX plane. The moment of inertia, I, of rotation in the ZX plane is really small, so we can neglect that other degree of freedom, so that for diatomic molecules we have 5 degrees of freedom, and for these guys we have 3. Converting this to the case of a diatomic molecule, 3 becomes 5. Okay? So we leave it at that, and now we'll head into where we wanted to go in the first place. And that is heat engines. What is a heat engine? A heat engine is a device for extracting mechanical work from a source. Call it a hot reservoir. Big Q. Okay? We can extract that and make it into mechanical work. And of course, work is force times distance. And I'm carelessly neglecting the sign here because of conventions. I'm leaving it up to Michel van Biesen for you guys to go and check his YouTube on what has he got now? Work, thermodynamic work, heat engines, a different view of it. Mine is kind of an overview and a little bit more mathematical. Okay, so this guy does a good presentation. I'm not going to reinvent the wheel, and the reason I'm avoiding it is because my convention is totally different than just about all the books you see. Yeah, my definition of the sign of mechanical work in a heat system is opposite to everybody else's. All right, so to avoid that confusion, I'm skipping it and letting him do the job. One way or another, for me, I just stick with this law by stating that this is the form of the first law that I will always use. When you have signs in this system, it's very easy to go wrong because you have choices of what we're talking about. Well, we can have work done by system, work done by our system, which is the piston cylinder arrangement, which we always have, or work done by the environment. Or we could have work done on either. There are two more choices. And then we're going to say, are either of these ones positive or negative? So we have 8 possible ways to make a mistake. Okay? So I'm going to suggest that you guys look at Fermi and follow him. You know, I'm not even agreeing with Fermi in some of the things that I've been doing, so I'm not going to argue. Fermi is the great mind, not me. Okay, so 8 ways to make a mistake if we're defining work. On or by, system or environment. What's the environment? The piston is its system and it moves against the environment, for example. We don't need this. We don't need any of this now. Now we look closely at the heat engine itself. So a hot reservoir, what we're going to do is be able to extract an amount of heat, delta Q hot. We're going to extract that from a hot reservoir. Sorry, we can do perfect circles when they're bigger, but when they're small, they end up being not so perfect. An amount of heat, delta Q, gets extracted. And another amount of heat gets delivered to the cold reservoir. Now remember, the reservoir is big compared to the deltas. So that's what the heat engine does. No, it does more than that. Suppose I get an amount of heat, delta Q, Q hot of 100 joules, and I deliver to a cold reservoir. I deliver how much? If I deliver 100 joules to this thing here, no mechanical work is done, right? But suppose I deliver 60, 80 joules. There's 20 joules missing. Well, the machine could have done some work. It could have done the missing joules. Mechanical work could have been done by converting delta Q, little delta Q, into joules, okay? 80 joules end up going to the cold reservoir. as well as the reservoirs, we need to have them at two different temperatures. Because the general idea says this, second law of thermodynamics, roughly speaking, says heat flows from a hot to a cold, what? Anything, substance, surface. Heat flows from the hot to the cold, and eventually the system will become in equilibrium. And there are two statements of the second law, one due to Clausius, which you guys can Google, you don't have to me to tell you it, and another one due to Thomson, and they play around with the words. I would like to be able to derive the second law using, and I might have a go at it because I have a rough idea of how to do it. And then Ludwig Boltzmann, he crops up much later. So look up Clausius's and Thomson's separate statements of the second law of thermodynamics on Wikipedia or something. But let's go back now to this heat engine. What do we need? We need the reservoirs. We need a reservoir at hot and a reservoir at a cold temperature so that heat can go from one to the other. T hot is greater than T cold. We need a temperature difference mainly. And a second law, heat flows from the hot to the cold. While we're at it, we'll just deal with this particular example. Now the 80 joules is a delta. It's a delta Q delivered. The delta Q hot is the extracted, but Q hot itself is a big huge reservoir. Q cold itself is a big huge reservoir. This could be the atmosphere. This could be the boiler in a steam engine. And we ask ourselves, how efficient is an engine? How efficient? Well, if we get all our, we have an automobile and we take, let's say, 2 gallons of gasoline in that, and we convert that 2 gallons entirely into mechanical work. It's all mechanical work. It's a completely efficient engine. Of course, in an automobile, engine is lost through the engine itself, friction within the components, inefficient combustion in the chamber, in the exhaust. Heat is thrown out in the exhaust, and then in transmission, huge amounts of automobile energy is lost through transmission. I have an idea for a transmission system that uses a lot less energy and is lighter, but I don't think that because the automobile manufacturers have their system. They like the gearbox. They like the differential assembly has to be there. But they like the gearbox, or they like the clutch, or else they like the automatic drive system, whatever it is, and it's all heavy. A lot of energy is lost. But we can see what the efficiency is here. 20 joules of work is done out of a possible 100. So it's 20%. Let's just write that down. Epsilon is the efficiency. So in our example, it's the work done as a ratio with the delta Q hot, the amount of heat extracted from the hot reservoir. But how did we get this? And these units are joules, so this is a ratio. We really just took the difference. What's the difference? 80 joules got wasted, 20 joules came out, and the difference is 20. Well, 20 over 100 is 20%. Which is just 0.2. actually going to write down this formula and keep it forevermore. The efficiency of an engine is 100 over 100, this is how we got it, over 1 minus delta Q hot, cold, over delta Q hot. So that's the efficiency of this particular case. In fact, this is the efficiency of any engine, and I'm going to write that down. As we need space, I'm afraid I have to get it off the board. Now you'll often see just Q cold or Q hot. I don't write it Q cold because that's the whole reservoir. Delta Q I'll stick with as notation. So that's the efficiency for any engine. Now, to get an engine to work, imagine this, we have our piston and cylinder. Now the piston could be driven by expanding gases, and the piston could be attached to a flywheel or something, and we get mechanical work done by rotating this thing here. There are state variables P, V, and T. And we always insulate our system so that heat doesn't escape through the walls. Now, Q and U are not state variables, neither is work. The state variables are the pressure, the volume, and the temperature. Now, the second law of thermodynamics will introduce a new one. Another statement of the second law, which I kind of like, is as follows. There exists yet another state variable, and this other state variable is called entropy, and it's very interesting. It's going to be the subject probably of a couple of classes. Okay, so the efficiency for any engine is this one. Now we're going to look very closely also at the Carnot engine. Let's check the time. The Carnot engine is the most efficient, and it's a theoretical engine. And the Carnot engine, like any engine, has to operate through a cycle. Suppose our system does work like this. Bang! We set it off and it expands and does some work, P delta V, and that's it, it stays there. We would like us to repeat this. We would like a piston to, work many times. So we need a cycle. And a cycle in a PV diagram could be like this. I suggest you go look at Michel van Biesen. He has a few different cycles, and he shows you how to work out the energy used up in a cycle, or put into the system, or extracted from the system. And it's equal to the work done by the system. Let's say we compress the gas, and we drive it through this cycle. Well, the work done is the area of the rectangle added to the triangle. If it was just a rectangular cycle, it would look like this. This cycle consists of change of pressure and no change in volume. Change of pressure and no change in volume. So no work and no work. But there's work done here and there's work done there by the system or on the environment, whatever way you want to look at it. One way or another, the magnitude of the work done is the area inside the box. So, to get a cycle and to get work from it, we need an enclosed figure. Now, it doesn't matter what shape you make it. Could be a figure like that, driven through a cycle in any direction. So we need an enclosed figure, and the Carnot cycle finds an enclosed figure of a certain configuration that delivers the most efficient, that is the most efficient kind of engine. Say the Carnot engine, and it's a theoretical one, and we're running out of time. We'll have to call it a day until the next class. In the next class, I'll look in detail at the Carnot cycle, okay? I'll also introduce the second law and entropy.